We're going to kick off the day with Celal and Ben talking about statistical data sampling.
No, you go ahead. You start.
So I'm Ben Greenberg, and I'm a graduate student at MIT. I'm concentrating in machine learning. I was an intern at Google for the past 2 summers, and this past summer I was working with Celal on statistical data sampling, which is what we'll be presenting today.
Hi, everybody. My name is Celal Ziftci. I am a software engineer at Google for the last 2 years. Before that, I did my PhD in University of California, San Diego, on software maintenance and testing. And I've been working at Google on those topics for the last 2 years. I've been building tools. So this is my 3rd talk at GTAC. I've been in the last 2 as well. Let's see what happens next year, if I can find something to present. So we're going to talk about today on a novel statistical data sampling technique on software testing. So I'm going to start by giving an overview of an important aspect of testing, which is data. So whenever we write test cases, as much as the code is important, data is also equally important, because that's what flows through our system, right? So one way of getting test data is handcrafting it manually. What do I mean by this? Think about unit tests. You have a deterministic set of inputs, and you send it through your system, and then you have a deterministic set of outputs, which you expect and assert against at the end of your tests. So this is one way of getting your test data, sitting down and putting down these inputs and outputs. Another way of getting test data is getting it directly from production. So sometimes we just don't have the time or the ways to get test data ourselves, especially if it's on a large scale. And in those cases, we would like to get it from production because it's pretty easy. So when I say production, just think about it like, say you have a system and you're collecting logs for all of your requests and responses. And this can basically be, say, 10% of all of the logs that you collected yesterday. And you can use this on your tests today. So, and this talk is specifically focused on sampling from production. So we're going to talk about some problems on this front and hopefully identify a solution for this problem. So I would like to show you some examples of the kinds of tests that you can have if you use production data for tests. So say you have an integration test, and you get some of your production data. As I said, let's say 10% of your logs from yesterday. So what you can do is you can just run through all of this data through your system, and then you'll get some kind of output. And you can investigate the output, and typical things that you would look at would be, does your system crash? Or do you use a lot of CPU? Or do you use memory? Does it get deadlocks? So kind of like black box kind of testing you can do with this data. Another example could be A/B testing. So there was a talk yesterday on diff, which is an open source tool from Twitter. So it was about A/B testing. So you simply get some production data. You have a current production binary, and you have your new version of the binary. And you can run the same exact data through these 2 binaries. And they produce some kind of output. And at the end, you just diff these outputs and figure out if there's anything abnormal. Some developer sits and looks and says, yeah, this looks normal. This is all fine, so we can push it to production. So these are the 2 kinds of tests that you can potentially have if you want to use just production data in your test cases. So something that's extremely important for these kinds of tests to be effective in catching bugs is that the sample that you choose from your production data should be good. So if you think about all of your data space in, say, your production data space, and if you can get a good sample of that, then there's a high likelihood that you should catch bugs, right? If there's a case where your system will crash, hopefully, if you get a good sample, your system will actually crash, and you will catch that during your testing. So assume this is a representation of your entire data space. And these blue dots are the samples that you choose from your entire production data. So if you look at these samples, you will see there are some middle ones, like the expected cases, and there are also some boundary cases, which you probably want to test. So let's make an analogy. So let's say you're a developer writing testing a function that takes one parameter, an integer, right? So you would probably test some positive inputs for it, but you would probably also test some negative inputs, some boundary inputs like max integer, 0, things like that. So this is pretty much very similar to that. So you want expected cases and boundary cases. So I'm going to give it over to Ben to talk about an example.
So now I'm going to try and ground this a little more in a distinct example that people might understand. Say your data looks like this. You have a bunch of people that you're trying to represent, and each of them has an age, a weight, and a height. And you might want to figure out, is there any problems in my system? Is there any age, weight, or height that might crash my binary? So you come up with a reasonable bound for each one. The age might be between 0 and 150. That's totally reasonable. But what if we have a person with an age of 0? We need to make sure that our system works for this. So you write a unit test to make sure that if age is equal to 0, nothing bad happens. We also might want age less than 0, because who knows what's happening? Maybe you're getting this information from another product somewhere else, and you just want to know, is there any case where age is going to break this? We might have ages greater than 150. Maybe someone's giving you that a person's age is 300, and you need to make sure that that's not too large for your system to handle. And all this is great. But if you're specifically going through these cases and saying, what do I think might break my system? What do I think might be wrong? What about the cases that you don't think about? What if age is null? If you don't think about it, you can't test for it. This is why we like the idea of sampling our data from production, so that we get the actual data that exists. And in an optimal case, we'd be able to cover all of these edge cases, whether we can think about them or not. So let's say that we have 500,000 of these protobuffers. A protobuffer is a Google data storage mechanism. It basically just has key value pairs. So in the example before, age would be the key. The value might be 50. So we have 500,000 of these. And in 25 of them, we have the specific case where age equals 0. So we're sampling our production data. And the common way that a lot of people do it is they'll do a random sample. In this case, we want to know how likely are we to catch this age equals 0 using a random sample from our data. And the results are basically that we need to take a tremendous chunk of our data to have a very high likelihood that we're going to catch one of these age equals 0 cases. If we only take 500 or 5,000 examples, we're most likely going to miss it. Even if we do 10%, which is what a lot of people in industry have been doing recently, we still have a 7% chance of missing this age equals 0 case. And if you think about having not just one field, not just 3 fields, but tens of thousands of fields, which is very common in Google, you're almost certainly going to miss this case if you just take one of these cases, if you just take 10% of your data. So from this, we can see that we pretty much need to take the entire sample in order to get a reasonable chance that we're not going to miss anything and we can be safe and confident in our new binary. So if you remember the picture that Jalal showed you before, we have a production sample, we run it through our integration tests, and we get an output. And if we take a massive sample, if we take the full 500,000 or 450 out of the 500,000, the integration test is going to take an incredibly long time to run. If it takes a full day to run, say, we can't run it all the time. We can't have it running with every change because it just takes too long. The same thing with A/B testing. Now we have the entire production data running through these 2 different binaries. We're getting their outputs, and we have this diff. But as Jalal mentioned before, a developer is probably going to have to go through this diff. And if we use all of our data, the diff is massive. The developer is going to have to waste a ton of time. It's going to be very tedious work. And at the end, there's a good chance that they're just going to say, yeah, it looks good to me, because they don't have time to go through 500,000 diffs. So what if we could get a small sample that covered the entire data set, that was representative of the entire data space, and made sure that we were catching all of the edge cases. The issue from before is that we both want a large sample for coverage purposes and a small sample for runtime purposes. We ran our statistic data sampler. So imagine that you have some data. And we wanted to actually sample this data. So the first thing that we want to do is we want to somehow reduce the feature space. We do this with what's called a data miner. This takes all of the features in your system and reduces them into a more manageable amount. If you have 10,000, it might reduce them down to 100, something that we can actually work with. And then we look at our entire new data space in this lower dimensionality that's easier to work with, and we start with a seed. The seed is where our sample is going to grow from. This is a random seed, but it's incredibly tiny, maybe 7 or 8 out of the 500,000 messages that we started with. And then we look at a new sample, and we say, does this sample teach us anything? And if it does, we add it to our seed and continue going. But if it does not, we leave it alone. And we continue doing that and adding data points slowly over time, but only important data points, only the data points that actually give us new information about what's going on in our sample space. And eventually, we populate the entire space. We cover all the edge cases, have a good representative sample, and that is what our data sampler does. So let's talk about some experiments. We ran this on 500,000 of our own production photos and managed to reduce that set to just 284 while covering all of the edge cases that you'd probably be interested in testing, along with having a smattering of these middle cases that you'd be interested in for just basic, does this work at all tests. We also ran it on a sparser data set. So that's what the 600,000 number is. These protos were incredibly sparse. They only had a couple fields each. And you'll notice that we were able to reduce them significantly further, because our sampler was able to figure out that there's only a few things in these protos that actually matter, and only care about those, which means we don't need as many to cover the data space. And then finally, our biggest success so far was that we ran this on 1.6 billion production protobuffers, reduced it down to 78,000. And this was from a Google team that was actually doing this A/B testing. Their tests were taking about 14 hours to run, and they were running them about once a week, because that's all you can realistically run a 14-hour test. We have them down to just a couple minutes, and they're now running it on every single submit. So we can guarantee that not only are these much smaller samples, but they cover all the expected cases and all the edge cases. The tests run much faster, and the diffs are a lot smaller and non-repetitive because we're not taking protobuffers that look all very similar.
Right.
So now I'm going to hand it back to Celal.
So this is basically what is called statistical data sampling in literature. So an example of this is the election polls. When you're trying to figure out which candidate is going to win, you go out and poll a bunch of people in the country, right? And it's very important to ask the question to the right people so that you can actually really get a good representation of the country, so that your success of prediction is high, right? So this is kind of a very similar problem that we're solving here. But one difference is that our feature space is very big. So as Ben mentioned earlier, some of these protocol buffers have tens of thousands of fields. So that gives you a very high dimensional data space. So we have to really work with this data space. So therefore, your features are really, really important. So if you don't have good features to represent your data space, you're not going to get a good representation of your data. Hence, as a conclusion, you're not going to get a good sample. So I can give you some examples of what these features that we're talking about are. So in that protocol buffer you saw, there were 3 fields, all integers. So for such fields, we can find the boundaries of such fields. We can say this field is always between 0 and 15, for example, right? And protocol buffers are open source, by the way, from Google. You can go look it up online. It's like JSON, XML. So basically, we take all this data, extract features from it. Another feature is we look at if a field is always null, never null, or it can be both null and not null. So we capture all of this information with our features. And given 10,000 fields, we might even have 80,000 features, because we look at every single field and we can actually extract multiple features for each specific field. And we also have what we call binary features. For example, we can say if this field exists in this protocol buffer, this other field should also exist. So it becomes pretty complicated very fast. So what I mean to say is we have a lot of features to have a good capture of our data space. So in the algorithm that Ben went over, we just showed you one example of a sampler. So we have 4 of these. The reason is different teams have different needs. The example that we showed you had the ability to capture both expected, like the middle ground cases, and the boundary cases. But some teams don't really care about the middle cases. They just want the boundary cases, right? So you can make small tweaks to the algorithm that we showed you, and we can simply just find boundary cases. And we can do basically similar tweaks so that we can get different kinds of samplers for different purposes. And finally, I think this is a very important point. So in our experiments, we showed you that we can do this on 500,000 protos, or we can do it on billions of protos. The reason is we can parallelize this with MapReduce. It really yields itself to parallelization. And I'll just go over quickly how that happens. So say you have all of your production data, and you basically shard this, meaning you split your data into approximately equal sized chunks, and then you use a separate data sampler to process that part of the data. And all of these data samplers are running independent from each other. So they don't know what protos they chose from each other. So they all yield some temporary sample, right? But the problem with this is, since they are working independently, they can actually have repetitions, right? And we don't want that. So what we do is we take all of these samples and then run them through another sampler again. And at the end, you get this final sample, which is equivalent to what you would get if you were to run all of this data serially using one simple data sampler. So this way, you can really increase the number of your shards depending on how much data you have. And given some time constraint, you can really process all of your data within that time constraint, regardless of how much data you have. Now, after all of this discussion, I think it's a very legitimate question to ask, how do you exactly know your sample is better than some random sample, right? How do you measure that? So we talked a lot about what happens if you get 10% of your production data versus what happens if you use this tool to get a very small sample that is smart, right? So first of all, as we mentioned, this is obviously going to be increasing the speed of your tests, right? Your tests are going to be running much faster, and the outputs are going to be a lot smaller. But another way of finding if your smart sample is good enough is you can simply run both the smart sample and the random sample through the miner, because the miner captures the essence of your data, right? And you can diff it and say, oh, my random sample was missing this, whereas the smart sample has examples of where that is missing. And this is what we did in our experiments. And the smart sample is obviously better. And an implicit or indirect way of doing this could be branch coverage. So when you use protocol buffers, there's a capability of generating an API for it, so that you can, say in Java, simply say get age, get weight. So it generates an API for you so that you can code against it, right? So in teams, they take some branch conditions based on these fields. So you can simply run both of these tools while you're instrumenting your binary and collecting code coverage, and see if your smart sample gives you better branch coverage. And this is an implicit or indirect way of measuring if this is still better. And again, obviously, we did this, and smart sample is giving you higher branch coverage in our experiments. So that concludes our talk, and we're going to open it up for Q&A.
Thanks, guys. So lots of questions. Starting off, how do you determine whether a sample introduces new information?
So we have this miner that we spoke about briefly, right? And what the miner can do is it tells us what the edge cases for any given sample is. So for an integer, because integers are pretty simple to work with, it might say that currently this sample has integers between 2 and 7. So then if, on some certain field. So then if we look at a new sample that has an integer of size 10, say, we know that this introduces new information because we can't possibly have value 10 in that slot yet. So we use this to determine whether or not we're getting new information from adding a sample.
And obviously, we're doing this in parallel. Like, we're not doing one field at a time, right? When you give us a new sample, we are looking at all of its fields all together. Even if a single field teaches you something new, we take that example. So,
can you tell a bit about the mechanics of the data sampler, i.e., how does it work? Is it a tool that we can use?
so basically, this data sampler, again, so you use the miner underneath, and the sampler is a pretty simple wrapper around it. You just mine it. If it's giving you new information, you accept the sample, and you keep growing your seed until you cannot learn anything anymore, and you process all of the data. Is this something that you can use? It's not open source yet, but since protocol buffers are open source, I guess we could open source this tool as well, the miner and the sampler. So yeah, it's something that we'll consider definitely.
What if you have an edge case that hasn't yet appeared in production data? How can you determine the production data set is complete?
That's a very good question. So this is yet another example of garbage in, garbage out, right? So if you don't have good production data, first of all, if you don't have good production data, you shouldn't be doing black box testing or A/B testing, because this is basically just trying to make that simpler, right? But yes, this is a very valid question, and this always comes up with the teams that we talk to. What happens is they run this not only on 1 day's worth of data, they keep running this until they do the next release. So basically, they try to capture new data over a period of time. So you don't discard your sample every single day. You just keep it, and then you keep adding more information to it as you have new features. And as soon as you have a new version of your binary, you start again.
And that's kind of a good point that he made also. With A/B testing in general, I think it's important to note that it only really works when you have a good binary running in production that has been going for a little while that you know works. Because if you don't know that your production one works, comparing a new one against it doesn't do you much good.
You partially answered this, but let's take another pass. How often do you update the sample set? How long does it take the sampling process take on 1.6 billion entries?
So I'm going to answer the second part of the question. So on 1.6 billion, I think we did about 100 shards, and it took about 4 hours. So you could basically just run it every day if you wanted. But you can have more shards, as I said.
Yeah, more shards just makes a little bit more overhead, but winds up taking less time because each sampler is going over less information.
And out of my own curiosity, are you putting the previously sampled data in if you run it the next day?
You can, yeah.
As like one of the inputs plus whatever new day's info?
Yes.
Regression tests are good when they catch errors before they are in production. I suppose this strategy cannot stand alone. Can you please elaborate on balancing this approach with scripted testing?
So obviously, you don't do just A/B testing, hopefully. You hopefully have unit tests, integration tests, which is pre-production tests. But it's always a good idea to also do kind of like canarying, which is what A/B testing usually is done for. So yeah, I agree. You should totally do pre-production testing as well.
And one really cool thing that this does is it actually, because we're running the miner anyway, we can actually tell you what a lot of your edge cases are. So we might be able to tell you a case that you didn't previously think of. Yep. And then you could go back and write unit tests for those if that's something that you would like to cover in a unit test.
Yep.
How do you choose a good sample?
Again, the features are the key pieces of information here. If you don't have good features, then your sample is also not going to be good. So that's kind of the most important part, I think.
How is the feature set reduced?
Feature set.
So we have this miner that we keep referring to. And basically what the miner does is it will go over everything and just figure out what the edge cases are for each field, or if a field even has edge cases. So if you have like a Boolean field, it might be true, false, and then if both things are present, we just will say, okay, that we have full coverage on this when we have a true and a false, because there's really no edge cases. Whereas for an integer, we might have an upper bound, lower bound. For a string, we might just have a list of possible strings, something like that. So we basically reduce it into just each field. Each field has something that matters about it, and we're only concentrating on the things that matter.
How do you know the edge cases for specific domains? 0 and 2 to the n might be edge cases for many scenarios, but one application might have edge cases at normal numbers like 2, 5, and 9, etc.
Yeah. So this is kind of coming back to the feature set again. So right now we have unary features, which are just features that you extract on a specific field by itself without any relation to any other field. We also have binary features where we capture the relationship between two different fields. But we basically stop at 2 cases because it becomes n squared. If you do 3, it becomes n cubed. So it becomes really intractable very quickly because, as I mentioned, some of these protos have thousands of fields, and it's just you can't deal with that kind of data. So this is actually a general problem about data mining, right? So when you're trying to do mining like big data, it's very important that you stop at some point before things get really exponentially expensive. Because if you try to do that, so let's just think about an ideal case. So ideally, what you're doing here is you're modeling the system that actually consumes this data, right? So the actual real representation is the system itself, the source code that you put in. What we are doing here is we are just abstracting that away by extracting these features using data mining on a lower dimensional space, let's say, right? And you can only go so far. And this is a very valid case. There might be cases where 4 different fields are very related. When something is, let's say, 5, the other one is supposed to be positive, and the other one is supposed to be true, right? So there can be all these relationships. You can have like Boolean logic in your protocol buffers, right? Like if this field is set and this is true, or if this is the case, that is the case, this implies the following, right? You can have really complicated structures, but those are very hard to mine, basically. So
we also notably have a field that you can set where instead of just doing ranges for integers, it will keep a list of all the integers we've seen up to a certain point. So you can set that so by default, I think it's 3, so it will only remember up to 3 values before it starts doing ranges. But we've tested with that as high as 1,000, I believe. So it'll actually, if there's 1,000 different integers that could be possibly there, it will keep track of every single one and try and catch one case of every one. Obviously, this grows your sample, but if this is something you're interested in, it is a setting that we have.
So yeah, this gives like more discrete values for your numeric fields as opposed to over-approximating very quickly. So.
And related to that, how do you handle and reduce non-numeric text data?
So we don't have anything specific for strings yet. There's research on automatically mining regular expressions for strings. We didn't implement that yet, but it's something we want to implement. So.
Yeah, and we do have the list thing for strings still.
Just keep the set of strings that have been visited.
Yeah.
And then we have like Booleans. We have, this is always true, this is always false, it can be either true or false, things like that.
And we have null checks. This is always null, this is never null. So.
Have you considered using these ideas to guide generative testing libraries such as QuickCheck?
Yes, so we have a project inside Google that is just starting to take these patterns that you find with data mining and then automatically generate samples. So in some cases, you can just go and take your production sample, right? But in some other cases, you can't do it because maybe there's a personal identifying information there. It's like user sensitive, so you can't actually take that. In those cases, you can just take these patterns that you mine, and you can automatically generate valid data, right? So this is another thing we are working on top of the miner.
What is the specific criteria for adding a new sample to the seed?
That we learn new information. Meaning, so it's very simple. You mine all of your data, and then you mine this one sample. If the patterns that you learned change even slightly, that means you learned something new. As simple as that.
And we talked about sampling strategy. Different sampling strategies basically choose this differently. That's the major difference between them.
Okay. Does it have a performance impact since you might have to enable debugging in the logs?
I mean, that happens before kind of we run this tool on stuff, right? Like many companies just have request response logging. We don't do it on all of our data. We do like 1% of the entire traffic for one day, for example. It depends from team to team, but yeah, obviously there's, but I mean, this is done selectively, right? Like you don't run it on all the time. You run it on for like 10 minutes, then you turn it off, and you do it over the day so that you have a good uniform sample.
And with that, I'd like to thank you.
Thank you. Thanks a lot.
Thank you.